All right, welcome. Good morning to the first full paper session of today. My name is Lars Linsen. I'm from the University of Münster, and I have the pleasure to be your session chair this morning. This is the full paper session on interactive dimensionality or high-dimensional data. I actually think I would prefer calling it multidimensional data, has a different connotation to it, but it's definitely about interaction in these high-dimensional spaces. And we have 6 very interesting talks, 3 of them giving in person, 3 being given virtually. If you have questions, I would like to ask you to put those into Slido, right? So please, you can already do that during the talk, put your questions there, and then people can vote on how much they like your questions. And then I can ask the most popular ones. Good. We also have a mic here in the room, so we can also do it old-fashioned. If someone wants to stand up and ask the question in person, I would also be fine with that. But I think it's easier if you start using Slido, especially also for those who are connected virtually today. Talking of which, we come to our first talk, which is given virtually. And this is the paper on rank access towards a systematic combination of projection and ranking in multi-attribute data exploration, and the presentation is given by Quan Li. So, please start the...
Hello everyone, my name is Changcheng Liu. I will introduce my paper rank access towards a systematic combination of projection and ranking in multi-attribute data exploration. Raw projection and ranking are used for large-scale and multivariate data that have their inherent constraints. Projection employs a visual metaphor of proximity is approximately equal to similarity, which means if 2 data items are near in projection view, their similarity in origin data. Users may want to identify clusters and outlines based on data observations, but specifying the borderings of data groups can be difficult. Actually, projection will cause loss information in the projection process. Projection generate a low-dimensional distribution that doesn't always accurately reflects the data relationship in the original high-dimension space. As for multi-attribute ranking, previous research have revealed 2 significant changes in its application despite its intuitive representation of order. One is about attribute contribution, which can explain ranking regions. Another is attribute weights. Attribute weights can affect multi-attribute rating results. However, users can hardly obtain a good set of weights to make final ratings. Our paper proposes a general method to uncover the connection between projection and the ranking algorithm. This method can be explored in model explanation. Here is our back-end engineer. In step 1, we use rank SVM to generate attribute weights. In step 2, we calculate the ranking score by attribute weights. In step 3, we transfer ranking to rating. In the ranking scene, attribute weights are important and hard to decide. Explores subjective feeling about the importance of attributes are complex and difficult to quantify, so we use rank SVM to learn explores experience. As we can see from A, this is bank ranking. If explorer adjusts bank 8 to rank 6, it means he thinks bank 1 to bank 5 is better than bank 8. So the difference of bank 1 and bank 8 are positive samples. When we use projection and ranking in the same environment, there are inconsistencies. If two data items are close in projection and far away in ranking, we think there are inconsistencies between projection and ranking, and vice versa. We use rating line to understand the ranking schematic in projection view. We get ranking by rank SVM, then we can draw rating average point in projection view, such as Guangzhou Bank is rating 3, but in projection view it is close to average of rating 6, not average of rating 3. So there are inconsistencies between projection and ranking. It means though Guangzhou Bank is rating 3 in rank view, its performance worse in projection. We use projection access to understand the inconsistencies between projection and rating. In view A, this is a projection view. Each yellow point is a projection point. The black line is rating line, and we can see D2 is close to average of rating 1 and average of rating 2. We think D2 performs better in projection view than rating view, so we use blue color to represent D2. D3 is the operator, so we use red color. Next, we will introduce our system interface and a case study by a video.
System interface. A. Data loader to facilitate data selection. B. Interactive projection view shows the projection distribution and guides analysts to explore the projection layout and directional semantics. We provide three kinds of ranking line generation methods: sequence ranking line, rating line, and self-define rating line respectively. Sequence ranking line connects each observation in the projected view in the order in which it is sorted from the best to the worst according to the ranking results of the ranking tabular view. Rating line connects the average observation of each grade according to the order of ratings. Self-defined ranking line allows users to lasso a series of areas according to their semantic understanding, and connects the average observations of all areas according to the order selected by the users. C. Ranking tabular view summarizes the attribute contributions to the ranking, and supports deducing the attribute weight vector based on user interaction, as well as compares different ranking schemes. A. Attribute legend. B. Data table with each row representing a data item, and each column representing an attribute. C. Save scheme button records the latest ranking scheme and the associated weight vector. D. Different ranking schemes are aligned horizontally for comparison. E. Attribute contribution area chart present result of rating computation. D. Comparative projection view analyzes the distribution of observation generated by different ranking schemes. E. Ranking projection axis view compares the results of projection and ranking in the same context. Ranking projection axis view consists of four parts: A. Projection axis. B. Score axis. C. Contribution axis. D. Attribute comparison view. User can resort to banks by clicking on the Align button for attribute similarity comparison. Case study. We show how E1 explores inconsistencies in predictions and rankings by loading the 2018 Chinese bank credit rating data into RankAxis. As shown in C, RankAxis divides the ranking list according to the attribute contribution distribution, for example, rating 1 for 1 to 4 and rating 2 for 5 to 11. Then, RankAxis concatenates the average observations corresponding to each rating sequentially to form a rating line in B. He further noted that in B, Guangzhou Bank has a rating of 3, but its actual rating is closer to the average observation of a rating of 6. That is, the distance from Guangzhou Bank to the average observation, with a rating of 6 is shorter than the distance from the average observation, with a rating of 3. The expert was quite curious about this observation. He consulted E and confirmed that Guangzhou Bank performs poorly in the projection, given the orange-red color. The expert further noticed that Dongyuan Bank with gray line has a rating of 6, and the two banks are pretty similar in the attribute comparison view. That is why Guangzhou Bank's rating is next to the average observation of rating 6 at E1. E1 think the ranking of Guangzhou Bank is unreasonable, so he compared Guangzhou Bank and the neighboring banks and found that the assets of the neighboring banks are greater than Guangzhou Bank. E1 wanted to put Guangzhou Bank down in order, then he compared Guangzhou Bank and the banks after it one by one to show is better than Jiangsu Kunshan Bank. Then adjusted Guangzhou Bank from 16th to 20th and clicked Save Scheme. After the adjustment, Guangzhou Bank's ranking drops down from 16th to 26th, while Dongyuan Bank's ranking rising up from 33rd to 31. E1 compared the rankings of the two banks with those of neighboring banks and indicated the results are reasonable. With this adjustment, the ranking distance between Guangzhou Bank and Dongyuan Bank have become closer, and the consistency of rankings and projections has been improved.
That's all. Thank you. So, any question?
Thank you very much. Are you here for the Q&A session? Can you hear me?
Yeah.
Yeah, great. There's one question in Slido. It says, can rank axis reveal inconsistency between nonlinear projection and ranking?
Okay. We use TSN as our projection algorithm, and TSN is a no linear dimension reduction algorithm. So I think we can discover they are inconsistent.
I would have a related question. So I was wondering whether it might be a good idea to actually use linear projections and then try to find the linear projection that best preserves your ranking order. Would that be an option?
Yeah. About this question, on paper discover the inconsistency between ranking and projection, and we can use different projection algorithm in this in our paper, and I think when we use different algorithm, we will lose some information. Actually, when we use different algorithm, we will lose different part of information. So I think the projection algorithm we use which projection algorithm is not important.
All right, thank you very much. There's one more question on Slido, but we have to move on to the next talk, so please answer that via Discord. So thank you very much again.
Okay, thank you.
We move on to the second talk of this session. This is called PC Expo, a matrix-based interactive axis reordering method for parallel coordinate displays. And it's given by Anshul Kumar Tyagi. So, please.
Hello, everyone. I'm Anshul Tyagi, and today I'll be presenting my paper on PC Expo. This is work with the Stony Brook collaborators, Tyler, Jeff Koenig, Professor Eric Zerdog, and my advisor, Professor Klaus Müller. So, a brief introduction on parallel coordinates. Parallel coordinates are great for visualizing very high dimensions of data because unlike dimension reduction techniques, they don't suffer from loss of information. However, there's one catch, like from a data storytelling perspective, the way we order PC parallel coordinates axis depends on what story we want to project in the data. So there are different ways to show the same information through parallel coordinates, and it depends on how we reorder the axis. You can basically change the story that you want to show from your plot. So now different line patterns in parallel coordinates show different pieces of information from the data set. So this is an example of 12 types of line patterns and the corresponding data properties they represent in parallel coordinates. Now, understanding this is very important because if we can control different line patterns and how they're displayed in parallel coordinates, we can control the story that is being shown through a particular axis in our visualization. So let's look at an example of what I'm trying to say. So this is in particular axis ordering of parallel coordinates, and I'm trying to showcase what different properties are highlighted in all these axis pairs. So the first one highlights number of clusters, second one convergence, divergence, followed by outliers, split up, and negative correlation. So you can imagine if we change this axis ordering, we'll showcase different properties in parallel coordinates. Yeah, so another example, looking at these line patterns, we're looking at a single axis pair in parallel coordinates. An important thing to note here is that all these properties can coexist on an axis pair, and they're found in local regions in our data set. So as you can see, this is an example from a cars data set. We're looking at an axis pair of miles per gallon and weight correlation, like weight axis. And as you can see, negative correlation is found on the lower end of this data. And if we look at another property, split up, it's spread across throughout all this axis. So this is all the 12 properties we just discussed and how they're spread across this pair of axes. And this happens throughout the data set if we consider every axis pair. So in this work, we focus on combining the coexistence of properties and localization together to create an axis reordering technique for parallel coordinates. So step one is to create an optimization function that will be used during axis reordering process. For example, in this case, I'm looking at clear grouping, positive variance, skewness as the properties that I want to look at my data. And following this, once you've created an optimization function, the second step is to decide where you want to look, like how much locality you want to use while deciding, while actually seeing where these properties exist in your data. So we can look at smaller window sizes, or we can increase the window size to look at higher levels of data from a much bigger perspective. And this is the type of heat map you get by choosing different window sizes. So we also considered previous works which try to optimize axis reordering and try to reorder parallel coordinates using all of these properties. But none of the tools support all these properties together in a single interface. Also, one important thing is the localization of axis. So local properties are very important when we're trying to reorder parallel coordinates, because let's say, for example, positive and negative correlation coexist on an axis. If I'm globally looking at that axis, then the overall value of correlation would be 0. But we want to look at it locally so we can note both the positive and negative correlations in the axis. So moving on from these limitations, we present PC Expo, which is a fast parallel coordinates axis reordering algorithm supporting localization and human in the loop. And you can control the axis reordering process with full explainability. You'll have the reasoning why you're getting to a particular result in your visualization. Let's do a quick demo. Just give me a minute so I can set things up. Wanted to do. Okay, perfect. So this is the hosted PC Expo. You can actually use it on your laptops if you want to, but I'll just showcase what the interface looks like and what all properties we can visualize with this tool. So right here, this is the main parallel coordinates display that'll show how the visualization overall looks like. On the right-hand side, we choose different properties that we want to optimize for. You can choose any of these properties, weight them on how much you want to look for these properties in your data. And this here shows an optimization function, overall accumulation of all the properties you've chosen on the right side. Now, when I can also choose a localization window size. So this basically means 90% of the range of each axis, and here I'm looking at 30% of the range of each axis. And based on what you choose here, this local view basically updates the window size based on your selection. So 30%, you'll see the 30% range of each axis. And when once you have selected an optimization function, you can just click on recommend, and this updates this heat map on the left-hand side, which is basically a calculation of all the optimize all these properties that you chose, weighted by your selection, and this is the overall score in your data set that you get, and you can easily visualize it in the heat map. Now, axis ordering works from here on. So once you have this pairwise distances in your data, you can basically do a global optimization here to get an axis ordering that basically optimizes on this heat map directly. So we do a traveling salesman on this heat map that visits each node once and maximizes the values of these sums that you've taken. We can also do axis ordering through this matrix directly, which is fully human control, and you'll know why you're getting to a particular endpoint. So I can just click on the matrix cell where I want to start my axis reordering based on the final values. And then you can choose next values based on the new results that you can see. So it only highlights the next options that you can choose. Simply just walk through the matrix, and you'll know basically because of the optimizations you chose, you have the results in your matrix, and you can end up to a final visualization that you want to showcase in your parallel coordinates. Different views, I missed this local view. So what this means is, let me reset this. So if you're looking at a matrix, and I can look at any axis pair in your data. So just click on any cell. This updates the local view here. And then you can select, you can see where all of these 12 properties actually lie on that axis pair. So I'm looking at body and flip length. This is a penguins data set. And this is positive correlation is found in this part of the data. And I'm looking at split up, which is mostly on the top side. So you can basically visualize all these properties locally, and then scatter plot here shows where these points are in your data set in a 2D scenario. Okay, going back to the slides, this was a quick demo. Now, all right, so now let's talk about how we detect all these properties locally. We basically implemented methods to compute all these properties in parallel given a data set, and some of them are fairly straightforward. So given a window size that you chose from the interface, we can calculate all these properties locally on the regions and generate the final scores for each of these axis pairs. So correlation is Pearson R, skewness is Fisher-Pearson coefficient, outliers are the z-scores, variance can be calculated with the covariance matrices. For fan and neighborhood, we use existing works to calculate parallelism and divergence properties in the data. For density change, we calculate KL divergence, basically measure how the distributions change from moving from the left axis to the right axis. And for split up and clear grouping, it's a different technique we used. It's called PCP-NR. You can refer to the details. I'll skip the details for simplicity in this presentation, but feel free to refer to it in the paper. So once we have all these calculated properties, it just updates the heat map as you saw on the tool, and then you can just reorder axis based on your liking. Evaluation and results. So that was the demo of PC Expo, and now we can look how PC Expo extends to the existing works and what improvement we have on this tool. So we did an extensive comparison of PC Expo via a user study of 10 users with an existing baseline tool called DRPC that is this is an parallel coordinates axis reordering tool using all the existing works, and you can just choose a technique and reorder axis based on this. So there were 3 different things we compared: time, number of operations used to come to a final visualization in parallel coordinates, and the score of the final axis reordering that we obtained. So, and the tasks, there were 3 tasks in the user study ordered by the level of difficulty. So task 1 was the easiest, task 3 was the hardest to get for the users. And looking at the time it takes with PC Expo to come to a final visualization of your constraints, it's much lower than the existing techniques because you have more control, you have local view and everything, so people can just look at the views and come to the conclusion faster. However, number of operations, the first 2 tasks had higher number of operations compared to the baseline tool because of the local view. People just interact more with the local view to make sure everything's right. And the final score, PC Expo has a higher final score compared to the baseline simply because you get what you want, and using local view you can basically understand what the final visualization is trying to communicate on each of these axis pairs. Also, another user study for usability study of PC Expo, we got consistently high scores on all the 10 usability questions. Looking at the SUS score, which is the usability score for a tool, we got above 75, which is the median usually. So this basically means PC Expo has good usability looking at the access reordering tasks from the user's perspective. Okay, so that was all for PC Expo. I can conclude with a few key takeaways. We present PC Expo, which is a real-time access ordering system, works for all the line properties, supports human-in-the-loop interactions, and is explainable with a localization approach. Thank you for your attention. I'm happy to take any questions.
Thank you very much. We have time for one quick question. It's actually one in Slido, and Jean-Daniel Faquet asks if correlation and anti-correlation, which are somewhat the same in PCP, you can switch the axes, so you can do them upside down. Are you using that feature?
We basically kept it for simplicity, so you can visualize it differently, but yeah, that's an option we can adapt. We don't have it at this point.
Okay, then thank you very much. This brings us to the third presentation, which is again going to be a virtual one. It's called Incorporation of Human Knowledge into Data Embeddings to Improve Pattern Significance and Interpretability. It's given by Ji Lee.
Hello, everyone. I am glad to present our VIS paper here on behalf of all the co-authors. The paper's title is Incorporation of Human Knowledge into Data Embeddings to Improve Pattern Significance and Interpretability. When analyzing a dataset, it is common to project all samples onto a plane and select specific visual structures, such as clusters and outliers, as candidate patterns. Ideally, a projection should have clear visual structures to facilitate pattern discovery. Moreover, samples in a visual structure should have any commonality, example, similar values on an attribute, to interpret who they refer to and how the visual structure forms. However, projections of most real-world datasets have significance and interpretability issues to some extent. They either do not contain clear visual structures, or the samples in visual structures lack commonality, making pattern discovery and understanding difficult. These two figures are the projections of two real-world datasets from which we hardly find any pattern. Subspace analysis is an effective way to improve pattern significance. Low-dimensional subspaces may contain clear visual structures unable to see in the original dimensional space. However, patterns found in the subspace that usually consists of linear combinations of original dimensions may not be easy to interpret. Many quantitative metrics of different principles can explain how visual structures form. However, they require users to select candidate visual structures in the projections, which can be difficult when the boundaries of the visual structures are not significant. Some conceptual models guide the construction of knowledge-assisted visual analytics systems. Many knowledge-assisted systems implement these models. However, knowledge in these systems refers to external databases or knowledge graphs, which are impossible to access for newly encountered datasets. Thus, we consider utilizing human knowledge to improve projection effects. We use three examples to explain the knowledge here. When analyzing a consumption dataset, we can know that men and women have different shopping habits. When analyzing a crime dataset, we can know that crime patterns are different on weekdays and weekends. When analyzing a traffic dataset, we can know that jams vary from place to place. We can conclude that analysts can always judge the existence of patterns associated with specific attribute values. These ideas derive from their experiences and appear in their mind spontaneously, namely the so-called tacit knowledge. We externalize the tacit knowledge by dividing all samples into groups according to their values on the attribute. We then use group indexes as sample labels and incorporate the knowledge into embeddings through a classification loss. By adding the classification loss, the projection has three changes. First, samples of the same labels cluster together, indicating their similar data features. Second, a few samples move away from those of the same labels to form outliers, indicating their distinctive features. Finally, samples of the same label form several small clusters, indicating the existence of subclasses. Anyway, visual structures become clear and distinguishable through knowledge incorporation. It is possible to incorporate incorrect knowledge, such as pulling samples with different features into a group. The knowledge thus pulls these samples closer. However, their different data features prevent the formation of compact clusters, making the influence neglectable. We designed an embedding network with a customized classification loss. Unlike widely used cross-entropy, our classification loss is to decrease intraclass distance and increase interclass distance, making the formation of visual structures easier. Moreover, the network does not have an encoder, thus having high efficiency. We integrate the embedding network into a visualization system that contains three components. Knowledge Editor achieves sample grouping to externalize tacit knowledge. Data Projector shows the projection. Pattern Explainer helps the analyst understand the visual structure selected from the data projector. We implement the knowledge editor as a tree. The root node represents the whole data, and the child nodes represent sample groups established according to the knowledge. It also integrates a control to facilitate creating groups through clustering. The data projector integrates a slider to adjust the ratio of the classification loss to the entire loss. The analyst can set a small ratio to observe which samples form clusters, indicating their highly similar data features, or a large ratio to observe outliers. The main body of Pattern Explainer is a factor list, where SHAP values of attributes gradually decrease from top to bottom. Thus, the higher a factor ranks in the list, the more vital it is in forming the selected visual structure. PE supports two types of factors. First, each dimension of the embedded data feature is an embedding factor, reflecting how the visual structure forms. Second, each value interval of the attribute for externalizing knowledge is a classification factor, reflecting who the included samples are. The analyst can click on a factor to generate a histogram that shows the value distributions of the samples on the factor. We apply the approach to two real-world datasets. For each dataset, we externalize knowledge on an attribute and compare the projections before and after the knowledge incorporation. We can see that clusters and outliers become apparent after the knowledge incorporation. The user study shows that incorporating knowledge into embeddings reduces completion time and operations since clear and class-consistent visual structures avoid blind sample selections. Quantitative experiments prove the advantages of the embedding network. Our embedding network generally has high training efficiency and can promote the formation of visual structures. In summary, our main contribution is a visual analytics approach that fuses human knowledge and machine intelligence via embedding for efficient pattern discovery. The approach involves an embedding network and a visualization system to form a knowledge-based exploratory workflow. Finally, we show the usage of the visualization system. We first import a dataset. Then we click on the root node. It represents the whole dataset. We select an attribute to create sample groups. The user can add a group by clicking to create a small rectangle. The control can automatically cluster samples into the specified number of groups according to their values on the selected attribute. We click on the button to generate the projection. The CLR is 0 by default to show the original distribution. We can increase CLR to incorporate knowledge. By doing that, visual structures become clear and class consistent. We lasso select two clusters and select the top two factors that lead to their separation. Two histograms show the distributions of the two clusters on the factors.
Should be, okay, now it's working. Thank you very much. Can you hear us?
Yes.
Hey, great. So there's one question in Slido, again from Jean-Daniel Fiquet. How can you separate adding knowledge and adding prejudice? Both we realize in the final visualization.
Our knowledge is a human experience, and is simple, and the introduction of knowledge is not to verify the knowledge, but to make the data patterns in the projection more obvious, so that more data patterns can be found. So we can use the knowledge and can find more patterns. So it's different to the projections. Yes, that's all.
Okay, thank you. Are there more questions? If not, then I'll ask a question. So you opted for training this to optimize this loss function. Did you consider embedding your loss function into something more traditional, like a multidimensional scaling? Would that have been an option? And why did you not decide for that, if it was an option?
Our classification loss can classification loss can use on different function. So we will use it to use it to show the projection. Our classification loss, compared with traditional classification loss, our loss tend to improve the intra-class similarities and reduce inter-class similarities of the symbols. And the autoencoder, the neural network is very it has reconstruction loss. It has reconstruction loss, and we use the network include classification loss and reconstruction loss to make the final embeddings simultaneously reflect simple similarities in the data features and classes. Okay, that's all.
All right, then thanks again.
Thank you.
We move on to the next talk, which is the last virtual one we have. It's on interactive visual cluster analysis by contrastive dimensionality reduction. And Zhaji Jia and Liangduang Wang are going to give the presentation.
Hello everyone, I'm Huang Ningquan from Central South University. In this work, we propose a contrastive dimensionality reduction technique for interactive visual cluster analysis, named CDR. Visual cluster analysis usually uses dimensionality reduction techniques and scatter plots to help users discover the clustering patterns of high-dimensional data. Many DR techniques employ a metaphor. Proximity is roughly equal to similarity. Thus, the data similarity is returned by the distance between their embeddings, and the data points scattered together can form visual clusters. But there still exist two gaps for a DR technique to better support visual cluster analysis. The first gap: visual confusions among clusters often occur. If the scatter plot is monochromatic, the clusters in the red dashed box can hardly be identified. The second gap is that how users steer the embedding results is unclear, because visual cluster analysis is a human-in-the-loop task. It lacks a universal ground truth. Modifying model parameter is the main interaction for current nonlinear DR techniques. So we want to design a novel DR technique to fulfill these gaps, and identify three requirements for the technique. They are present trustworthy visual clustering patterns, present clear visual cluster separation, and support effective user steering of the embeddings. But it's not an easy task. To present trustworthy clustering patterns, the DR technique needs to correctly construct the neighborhood structures and faithfully preserve them in the embedding space. The k-nearest neighbors is widely used to represent the neighborhood structures, but they may have mistakes due to improper similarity metric and k-value. And to preserve neighbors faithfully, there also comes the problems of missing labels and false labels. As for presenting clear visual cluster separation, it's a trade-off with the first requirement. Separating clusters in the embedding space will destroy the neighborhood structure if two clusters are not well separated in the high-dimensional space. In terms of supporting effective user steering of the embedding results, current interactive methods are neither intuitive nor directly related to clustering. An intuitive interactive nonlinear DR technique is worth proposing. To fulfill these requirements, we propose contrastive dimensionality reduction, named CDR. Firstly, contrastive learning is introduced into dimensionality reduction. This helps better preserve the neighborhood structures and present trustworthy clustering patterns. After that, we propose a gradient redefinition technique to improve the visual cluster separation. Finally, we introduce link-based constraints to support effective interaction. Here is CDR's pipeline. For each point, CDR will sample a point from its neighbors, forming a positive pair and sampling other data to form negative pairs. The embeddings are then computed by a neural network, and the network will be trained with a contrastive loss to pull the embeddings of positive pairs together and push apart the embeddings of negative pairs. After that, the user can add master links and can-null links to steer the embedding results. Let's firstly look at how to present a trustworthy visual clustering pattern. The main inspiration comes from contrastive learning, which is a self-supervised representation learning method. It pulls similar instances together and pushes dissimilar instances away to learn effective embeddings. The similar and dissimilar relationships are represented by positive pairs and negative pairs respectively. It has a strong discriminatory ability. We want to leverage this ability into dimensionality reduction. In order to preserve the neighborhood structure, we construct positive pairs based on the k-nearest neighbors. For each point, we sample one point from its k-nearest neighbors based on the neighbor similarity to construct a positive pair. All data except itself and its positive counterparts are considered as negatives. We randomly sample from them to construct negative pairs. The embeddings are then computed by the network, and we use NT-XENT contrastive loss to train the network. Compared to the widely used cross-entropy loss, NT-XENT has an increased penalty when dissimilar data have similar embeddings. Thus, the network will learn a more separated embedding for dissimilar data, such as the false neighbors. With the k-nearest neighbors-based positive sample strategy and NT-XENT loss, we can correctly preserve the neighborhood structures and present a trustworthy visual clustering pattern. but two clusters may still be close together. We need to further improve the visual cluster separation. The gradient curve of NTX-ENT shows that the no similarity negative pairs have a minimal impact on the model update. In fact, they usually come from different clusters. So our intuition is that if we can increase their contribution to the model update, then we will be able to extend the distance between different clusters in the embedding space. But the challenge lies in determining which negative pairs to increase gradient and how to increase it. A too wide or too narrow range cannot present real visually separated clusters. Therefore, we determine the range based on the training statistics information of CDR on 25 real-world datasets. We found that when the similarity is less than 0.1, the negative pairs mainly come from different clusters. The next question is how to increase the gradient. The NTX-ENT shows that an exponential gradient curve works well in separating dissimilar data. We thus would like to add a similar but smaller continuous distribution to the gradient in the no band of the similarity to separate clusters. Therefore, we choose the positive skewed distribution, which is similar to the exponential distribution on its left. Adding it to the gradient curve of NTX-ENT loss, we get the redefined gradient curve of negative pairs. Thus, we can achieve clear visual cluster separation. Next, we further introduce link-based constraints into CDR to support effective user steering of the embeddings. Link constraints are widely used in interactive clustering, where master link indicates that 2 points should be grouped into the same cluster, but cannon link is the opposite. Compared to previous interaction methods, it is convenient to leverage the user's instance-level knowledge and is directly related to clustering. After users specifying link constraints, CDR will incorporate them and further optimize the embedding results. Thus, we can support effective user steering of the embeddings. We then conduct several experiments to evaluate whether CDR can meet all these three requirements. In the quantitative experiments, we select both parametric and non-parametric techniques for comparison, and conduct experiments on 10 real-world datasets. From the scatter plot results, we can notice that different clusters are well visually separated in CDR. The numerical results show that CDR achieves performance comparable with TSNE in trustworthiness, but it doesn't perform well in continuity, as the calculation of continuity includes false neighbors. Removing them in the embedding space will decrease the continuity. The results on k-nearest neighbors classifier accuracy and neighbor hit also demonstrate CDR's improved neighborhood accuracy and ability to correct false neighbors. In terms of visual cluster separation, the results show that CDR outperforms all other techniques in distance consistency and Seglut coefficient. The results of ablation experiments verify the effectiveness of the NTX-ENT loss and the gradient redefinition technique. In the user study, we propose two hypotheses to verify whether CDR can help users identify clusters more quickly and accurately. During the experiment, we provide users with a monochrome scatter plot each task, and ask them to circle the clusters. The results show that CDR is significantly better than TSNE and UMAP in terms of identification accuracy, but in terms of the speed, CDR is significantly faster than TSNE but comparable with UMAP. In the case study, we verify the effectiveness of the link interaction from two perspectives. First, we perform reasonable interactions and found that when the added links are consistent with the data features, one link is often enough to achieve the user's purpose. In the video, the two clusters in the upper left corner represent the butterfly images dominated by the foreground and background. Only one mask link is enough to merge them. It verifies the efficiency of the link interaction. And we also wonder how CDR would behave for unreasonable interactions. We try to use mask links to merge two dissimilar clusters, the chickens and dogs. But it often requires 3 or more links. The first two mask links only slightly bring the two clusters closer, until the third mask link merges them. This demonstrates some degree of resistance of CDR to bad links. To sum up, we propose an interactive visual cluster analysis approach in this work. We introduce contrastive learning into dimensionality reduction, propose a gradient redefinition technique, and enable link-based interactions on the embeddings. The experiments and user studies show that the proposed CDR can present trustworthy and well-separated visual clustering patterns. Case studies demonstrate the effectiveness of the link-based interactions. And it's worth noting that CDR is the first parametric DR technique that can achieve comparable embedding quality with TSNE. That's all of my talk today. Thank you.
Thank you.
Yeah, can you hear me?
All right. Yeah, we can hear you well. Okay, great. We have two questions in Slido. The first one is again by Jean-Daniel Fouquet. He wants to get the most active questioner award today. The question is, the method might be sensitive to noisy points. Several clustering methods like HDB scan try to remove the noise before optimizing the clusters. Is it also a problem with your method?
Oh, yes. There also exists noise data in our data set, but in many represented as the outliers in the scatter plot from the main clusters. And also we mainly focus on clustering tasks. Users can also correct this noise data by adding master links or canal links to assign them to their correct clustering clusters. Yeah, thanks.
Okay, thanks. And there's a second question by Wei-Jing Lin asking, what is the major difference between using deep learning methods for projection and the general representation learning task?
Representation learning usually focuses on learning high-level and abstract features of data, such as semantic information between instances or classes, rather than preserving the original high-dimensional structure of the data. This is the main difference between representation learning and the data dimensionality reduction. And it's not an easy task to leverage neural networks in dimensionality reduction and achieve quality embedding comparable with the leading non-parametric techniques. And our method is the first one. Thanks.
Okay, thank you. There's another question on Slido. I would ask you to answer that by Discord due to time. So thank you. Thanks again. We come to the next presentation, which is given in presence by Cristina Marario. It's on predicting user preferences of dimensionality reduction embedding quality. And whenever you're ready, you may start.
All right. Hi, everyone. My name is Christina, and today I'm going to talk about this project I was working alongside René and Michael from University of Stuttgart and Adrian and Benoit from University of Namur. The project is called Predicting User Preferences of Dimensionality Reduction Embeddings, or unofficially Dumbledore. So in recent years, there's been a lot of research on dimensional reduction, and there's a lot of techniques being proposed out there, which is cool, but also like a burden of the users, because what should they choose? And research showed that when people apply dimensionality reduction techniques to their data, they don't really care too much what is the specific quality of the technique, and they apply it in a black box way, so they will do something like that. And then this one will make it to the slide deck. So the question that we want to ask is, like, can we spare users of this grid search process and select for them what they want? And then is what users like something that is really predictable? So we're not the first people who thought about that. This group, Louis et al., they wanted to see if people's preferences are really reliable. So they took like a bunch of data sets well known in the literature. They computed a lot of embeddings for all of them, and then they asked both novices and experts what they thought. And then they found out that experts had reliable judgments, but novices not really. And this was mainly to do with the fact that novices were not familiar with these data sets that are extensively used in literature. So they were like, okay, we're not trusting these people. At the opposite end of the spectrum, there's like other work where people took 18 images, 18 data sets of images, text, tabular data. They generated a lot of embeddings for those as well, and then they calculated metrics to assess quality. So upon some analysis, they came up with this recommendation that methods like TSNE are best on average, so people should just use those. So our work is kind of in the middle of this in the sense that we care both about metrics and user preferences and kind of try to form a bridge between two things. So we ran this experiment where we wanted to analyze if we can predict preferences of non-experts as well on a lot of different data sets with some quality metrics that already existed. So the talk is about how we did that. So we took 11 image collections, and we generated embeddings relating to 7-dimensionality reduction techniques. We crowdsourced user preferences and generated metrics for each embeddings. And then we trained a supervised machine learning model between the metric space and the user preference. And we'll see what we got. So what did we choose? Image data sets. We wanted to provide users access to the high dimensional space. So that's the image and the actual pixels. You don't need to be an expert when you want to understand what's going on in an image. And then you have access to the low-dimensional space via the scatter plot. So we had all kinds of image collections, like things that toy data sets used in literature, but also photos of buildings and things collected from Flickr and so on. And across the study, we asked people how hard it was for them to familiarize themselves with this data set. And different data sets were easier than others. And this is reflected also in how user preferences were aligned. Like if a data set was easier, people tended to agree what's a better embedding. But if a data set was perceived as harder, there was more disagreement in there. So before we dive more into that, the dimension reduction techniques we chose were what's popular in literature these days and parameterizations of them. And then we generated about 25 embeddings for each data set, and each user had to score 8 of them. Then we ran this crowdsourcing study where we gave people points, and they were looking at these dimensionality reduction embeddings, and they had to distribute these points to them and like make opinions of what's better and what's worse. So every time a scoring would go on, the person could like sort their embeddings and like check what's up. And then users could alternate between 2 different views. So this view where you had scatter plots and images, and then scatter plots with like just color-coded classes. We had 54 users rating each data set. They came from all walks of life. Some people didn't even know what dimensionality reduction was. So the metrics we chose were accuracy metrics. So these are like the stress metrics that you usually find in dimensionality reduction techniques as optimization losses or stuff like that. Skagnostics, which measure patterns in scatter plots, and separability metrics, which are visualization metrics checking adherence to labeled classes. So we trained 3 models. The easiest one was predicting if an embedding is good or bad. The second was if an embedding is better than another embedding. And then the third one was predicting a whole like ranked list of data. And like the difference between this and the previous model is mainly that this one was a nonlinear model. So yeah, the easiest task did the best. We got like 90% accuracy. And then the third task was kind of finding a sweet spot of performance and task difficulty trade-off. We evaluated this on leave one data set out. So this is a cross-validation setup where, for example, for this data set shown here in the image, we trained the model on all the other data sets, and then we only evaluated on this one. So we can see, for example, that if you have a data set like MNIST, where half of the people thought, oh, this is easy, the model was performing very well. But then when you have another data set like Yale faces, where people are displaying emotions, people were like, oh, this is hard, and the model also did not like those embeddings. So going back to model 3, one extra thing it outputs. There's like a score that tells you how good, from a qualitative perspective, this model is. So it's not just whether it's more preferred than others, but like absolute quality. So we took this and we made like this really cool visualization where each point in the scatter plot is one embedding, and then each color of this dot is a dimensionality reduction technique. And then on the left-hand side, you have the top 3 highest rated predictions in this data set. And then the color of the background is this interpolation of the ranking score obtained from model 3. So what does it mean? For example, in Emily's data set, there were a lot of good embeddings. So you have like this part of the space is really blue, but then you have this data set of paintings where the dimensionality reduction didn't work as well, and the model is just telling you out these embeddings are kind of bad. So you can also assess for yourselves qualitatively the embeddings on the left, on the right are not that great. So there's more fun interactive viz of the data sets that we used and potentially your data set at this website made by my colleague Renee. Knock yourself out. Yes, so what were the best metrics? This was interesting because as it turned out, the accuracy metrics were not really that useful, but for the model, like the model used agnostic, used probability metrics, stuff like that. But we speculate that it's not because people don't care about or like don't notice misleading patterns. In our data set, there are no misleading clusters or like clusters with mixed classes and so on. So it kind of, we're speculating that this means that aesthetically pleasing embeddings are kind of an indirect signal for accuracy, just not as strong one as the metrics that measure patterns. So yeah, that's it from me. There's more fun discussions in the paper. The code and the data is available. Thank you.
Thank you very much. So let's start with one question from Alex. He's asking, your evaluation seems focused on embeddings of images. What would you expect for other data types, such as tabular data, language, etc.?
So the reason we went for images was because we couldn't easily visualize the high-dimensional space. I would expect it for text to be easy, but in order to prove it, we would need to do, like for tabular data, some sort of glyph visualization. And in that case, it's much harder to have access to people who are not familiar with glyph visualization. So can't really tell, but fingers crossed.
Okay, maybe I have a related question to that. So you opted for like users with like no experience. Was that mainly because then you can get a large crowd of people, or was there another reason why you didn't include like people with expertise in some field?
So it wasn't only people with no expertise. There were people that were dimensionality reduction researchers, but there were also people that never heard about this. And I think we just tried to get a representative sample of the population. Yeah.
Did you look into whether people with different expertises had different responses?
Yes, we did look, but there were no major effects. The effects were more on the dataset level. So when the dataset was producing worse embeddings, these were universally disliked. Like even the experts were not agreeing with each other because the results were kind of random. Yeah.
Okay. If there are no further questions, then let's thank Christina again. Thank you very much. And we come to the final presentation of this session. This one's given by Eric Cuenca, and it's called Vertigo, a visual platform for querying and exploring large multi-layer networks. So, please.
Hi. Hello, everyone. Thank you for being here. My name is Eric Cuenca from Yachak Tech University, and I'm happy to present the system called Vertigo. It's a visual platform for querying and exploring large multi-layer networks. And these works come from my PhD, where I collaborate with my advisor at that time, Arnaud Salaberry, Dino Yenko, and Pascal Poncelet. First of all, a short description about graphs. As you know, they are a structure that capture relationship between entities. For example, this figure shows a node link diagram where the circles are the entities and the relationship between them, the lines, are represented by the edge. So a graph can model a lot of real-world data. For example, a social platform like Facebook where people are connected, or a node-short link structure where the entities are linked, or a biological network where the entities are proteins and the edge represent the interaction between them. Now imagine your closest friend on the Facebook platform. The people are the graph entities and the edge represents a friendship relationship between them. So we can easily highlight with this structure the person with the most friends. Now, what if we want to represent the friendship connection through three different social networks, Facebook, and Twitter, and LinkedIn? So in this case, we should use a different graph for each network. However, using a multi-layer graph is a better way to represent this information. Multi-layer graph allows definitions of multiple types of node and edge. For example, we can merge in one structure, in a multi-layer graph, the three social networks in just one structure, one graph structure. So each edge is colored according to the social network it represents. For example, Facebook in blue, Twitter in green, and LinkedIn in red. But most of the time, multi-layer graphs are big, are large. So they are composed by thousands of nodes or edge. So a common question arises about how to extract knowledge from these kind of graphs. In this context, the subgraph matching technique is an approach that helps us to obtain information from graphs. It consists of searching for all occurrences of a subgraph in the target graph, in the main graph. So most of the time, the subgraph is called a pattern. We will start the query process by sending a pattern, a subgraph query, to the target graph. Each occurrence of the pattern is called an embedding. We can use the selected, we can see how the selected embedding has the same pattern of the initial subgraph query. That is the same number of nodes and the relationship between them. This is another embedding. Note how entities from the previous embedding are present. And this is another embedding. So at the end of the query process, we may have a lot of embeddings, a lot of results. Along with the subgraph matching technique, there are 4 tasks that graph query system must perform. They are query construction, result visualization, result exploration, and query suggestions. The first task is related to how to design, how to construct the initial subgraph query. The visualization of result is related to how to display the results. In this task, several challenges arise. For example, how to use a convenient graph layout to visualize thousands of nodes, or how to deal with the subgraph isomorphism problem to find all the occurrences of this pattern in the target graph. The third task involves rendering the results at the different levels of details. That means allowing topological analysis of the result, individual results. And the final task is the query suggestion. In this task, the initial subgraph can be refined using the target graph, the big graph, and the result already obtained. This table shows a comparison of different visual graph query systems. We can note that all systems support the first 2 tasks, query construction and result visualization, but few for the last 2, result exploration and query suggestion. It is worth mentioning that our work supports the 4th task and also works with this kind of graphs, the multi-layer graphs. I present to you the Vertigo system. It is composed of three main views. The first one, the query view, allows the user to interactively define the query structures. I mean the node, the edge, and the node attribute. The second view, the graph view, shows the target graph and either a heat map of the embedding location or a visual representation of single embeddings. Finally, the embedding view shows a list of embeddings for a set of selected nodes. Also, this view details the topological structure of the selected embeddings. I will demonstrate Vertigo. To do that, I will use a multi-layer co-authorship network from the DBLP website. And this network is composed of 38K nodes representing the authors, 130K edge representing the co-authorship relationship between them, and 18 layers representing the venues of the viz and data mining fields. The pattern to look for, I mean the subgraph query, will be the author who acts as a link between them in the viz and the data mining communities. So for example, here, he or she published a TBCG paper with one author, and he or she also published an ICDM paper and a KDD paper with another author. So we were looking for this pattern. We start to construct the query via interactivity functionalities using the query view. It supports drag and drop operation, and it allows the user to specify a node attribute. The user can start the query engine to retrieve the results. A heat map shows the location of the results, and the process can be paused and resumed at any time, allowing the user to explore partially collected embeddings. Vertigo allows to refine the previous query. Dashed line depicts new internal relationship, and new external relationship are depicted by the slices of a pie chart, where the area represents the percentage of new embeddings that can be extended from this node. In this example, we add the information visualization venue as a new relationship and run the query engine again. Guided by the heat map, the user can zoom into a region of the target graph. The size of a node represents the number of embeddings where it belongs to, and we can focus our attention on a determining node looking by their name. For example, the name of an author. Based on the size of the node, we select the author Daniel Kine and N. Ramakrishna to get all the associated embeddings. A KEL-based visualization allows the user to visualize a selected embedding where each result is assigned to a colored layout. We know that when node or edge are involved in many embeddings, they become visually dominant. These diagrams are free overlapping, have flexible configuration, and the user can easily interact with them. Following the structure of the initial pattern, we can see that the author N. Ramakrishna acts as a link between the viz and the data mining communities. In summary, Vertigo supports tasks commonly involved in the visual query process. I mean query construction, visualization and exploration of query result, and query suggestion. As well, Vertigo interacts with the query search engine, allowing the user to start, pause, and resume the query process. And Vertigo combines visual components and interaction to analyze the result at different levels of details. You can find more information about Vertigo, including the paper, this video, and the source code at the following link. Thank you for your attention, and I will be happy to ask your question.
Thank you. We have a lot of questions for you. So let's start with the first one. Actually, the first two are very related. The first question is from Ameya Patil. How big a graph can Vertigo handle? Some comments on the scalability. And then the second one from Anjul Tyagi is, how do you store the multi-layered graph internally? So I think these questions are related.
To answer the first question is, how big graph can be used by Vertigo? So this is This is not a website. This is not a web platform. So we can test with a graph of 100 of nodes. Okay, so it deals really well. But I will say that it depends in the configuration of your local machine. And can you repeat me?
How do you store it internally?
Sorry?
How do you store your graph internally?
Okay. We use the GML structure in order to load the graph structure. So we can easily export to another graph query system.
Okay, there are more questions. I will ask one last one. The rest, please ask them on Discord. Answer on Discord. Jan Arts asks, the tool is very interesting for single queries. Is it possible to compare the results of multiple queries?
Okay, for now, no. But this is an interesting question. So this is probably for our future work because we can save the initial query, but we cannot save the result of this query in order to compare with another query. So we will take this idea for future work.
All right, then let's thank Eric again and all the speakers of this session.